Hello guys, welcome back to my channel. Today is day 2 of covering electronics, and today we will cover electric current from very basic and in an easy manner so that everyone should understand the electric current from very scratch. So we'll just start with it. So inside any copper wire, the physical reality of electricity in chaotic but highly directional. Billions of negatively charged free electrons constantly surge through a lattice of copper atoms, moving rapidly from negative terminal to the positive one. But if you look at a standard electrical design diagram, you will see something entirely different. The arrows depicting conventional current flow are always drawn pointing into the exact opposite direction from positive to negative. That means the arrow on our blueprints point completely contrary to the actual flow of physical matter inside the wire. This contradiction traces back to the Benjamin Franklin. During his pioneering working in early electronics, Franklin established a conventional that assigned positive charge signs to whatever mysterious force was moving through the wires. Franklin's positive current convention was already deeply entrenched in scientific calculations. Rather than rewrite all the established laws of physics, electrical engineering relies on deliberate mathematical abstraction. We are going to explore why pretending current is made of positive charges mathematically works flawlessly and how engineers use differential calculus to model this abstract current exactly as it changes over time. These experts list are physical constants. An electron and proton have equal but opposite charges of 1.60 times 10 to the negative 19th coulomb. Calculating the physical number of electrons from 1 ampere current hits a snag. The equation outputs a negative quantity. You cannot have a negative quantity of physical particles flowing per second. It makes no physical sense. To resolve this negative sign, we are left with the two options. Either physical electrons are moving in the opposite direction of the definite current, or positive charges are physically moving through the wire. Positive charges are locked in the lattice, so physical negative electrons move left. Mathematically, replacing the negative charge with the theoretical positive charge and reversing its vector means a negative moving left balances a positive moving right. This concept is formalized in figure 2.3 of this textbook, which directly compares this dual direction model of conventional current flow pointing right versus physical electron flow moving left. This is the golden rule of electronics. All the standard formula pretend current is made of positive charge carriers. We accept this convention because it maintains perfect mathematical symmetry with physical reality. With the direction resolved, we need to measure the quantity of the charge moving over time. This text defines average current algebraically as the total charge delta Q passing through a specific cross-sectional area over a given time interval delta T. Looking closely at example 1 here, we can see this applied if a conductor carries 2 ampere over 3 seconds. The product is 6 coulomb of charge. To put that in a perspective, 6 coulombs represents a massive discrete block of physical matter, specifically over 3.74 times 10 to the 19th electron. But in modern electronics, current rarely sits at a clean steady state. It fluctuates constantly. To track fluctuations, we use the calculus concept of taking the limit. We take our time interval delta t and shrink it closer to zero. This transforms our average rate into an instantaneous current defined mathematically as the derivative I dq over dt. While algebraic averages give us a broad view, this differential calculus is the mandatory tool for the modeling how current actually behaves moment to moment in dynamic real world systems. Let's look at the scenario where charge is changing sinusoidally over time in a functioning circuit. Example 2 provides the specific equation for this. The charge function q of t defined as a 0.001 coulombs times the sine of 1000 t. To find the instantaneous rate of a change, we take the derivative of this sine function. Differentiating the sine wave generates a cosine wave representing actual current flow. Analyzing the system at exactly 1 second, the instantaneous current is positive 0.174 amperes. Jumping forward to 3 seconds, the curve dips, reaching a negative zero point 0.5 amperes. That negative result has a specific physical interpretation. It indicates that the current has reversed its direction of flow in the wire. This negative sign in a differential context is the mathematical signature of alternating current. Our derivative model tracks this physical direction changes automatically without us having to alter the questions. So daily current operates on a vast logarithmic scale, starting down at the level of picoamperes and microamperes. At this extreme low end, advanced microchips operate on a fraction of millionth of an ampere. Moving up the scale, typical consumer electronics like smartphone draw heavily in a hundred of milliamperes. We cross the 1 ampere threshold when dealing with common household appliances like light bulbs or electric fans. Looking closely at the textbook breakdown here, we see the critical danger zone. It only takes between 100 milliamperes and 1 ampere to induce a cardiac or respiratory arrest in a human. Above that, we hit the hydro range. The microwave pulls up to 13 amperes and an automobile starter requires around 200 amperes to crank an engine. Then there is an extreme upper limit of naturally occurring current. On Earth, a single lightning strike breach the 1000 ampere threshold. Whether it is fraction of microamp or a massive atmospheric discharge, we abstract the physical electrons into conventional positive current simply to maintain the mathematical utility. We then